We hosted Nadav Cohen. He did his PhD in Jerusalem with Amnon Shashua. He's now in Princeton with Elad Chazan in Sanjay Aurora. And thank you, Nadav.
Thanks. Thanks for the introduction. Before I start, just to get a little bit of a sense of the crowd, how many people here know, work on something related to deep learning, or know what a convolutional network is, what the structure of a convolutional network is? It's about half. So I'm going to try and address both crowds here, those that are not intimately familiar with the field and those that are experts. Hopefully you'll all get something from this talk today. The title of the talk is On Optimization, Expressiveness, in Deep Learning. Okay, so at least half of you know that deep learning is the greatest thing ever. It's true. It is a great thing. It's transforming a lot of application domains.
The deepest thing.
Deepest thing. Okay, so it's transforming a lot of application domains, works really, really well, and is really changing our lives as consumers. What I assume many of you also know is that this technology has a dark secret, deep dark secret, and that is that we don't know what's going on there. Okay, we don't know why these models behave the way they do, which models are better for which problems, and many people, myself included, believe that it is important to understand this technology for several reasons. First and foremost, maybe scientific curiosity. Also, a little bit more practical, technologies that we understand tend to work much better than ones we don't. And finally, these type of models are entering application domains which are critical. Okay, infrastructure or health. And the last thing you want is an algorithm that you don't understand, making a decision that you don't understand, and costing human lives. And so hopefully we're all convinced that understanding deep learning is important. I will start by kind of personal reflection on what it means to mathematically understand deep learning. What are the basic questions? This will be very, very high level and inexact. For those that are experts in the crowd, please don't throw anything at me. I will be more kind of precise when I talk about my actual works in the second part. Okay? Okay, so if you want to formally reason about deep learning, you have to start with statistical machine learning, because at the end of the day, deep learning is a special case. And we're going to lay out here the basic statistical learning setup. Okay? So we have X. This is our instance space. That's the set of objects that we would like to infer something about. Okay? For example, 100 by 100 matrices could represent 100 by 100 grayscale images. The value in the elements correspond to pixel intensities. The instance space could also represent audio recordings through vectors or anything else. We have a label space, Y. That's the set of possible labels that we could assign to instances. Okay, so if we're measuring some continuous property of an image, then Y could be the rails. Or it could be 1 through K if we are classifying the image into one of K categories. There is some distribution over labeled instances. Some distribution that characterizes the world. We do not know this distribution, but we do assume that it exists out there. And finally, the last property of the world, of the problem, is a loss function. Okay, this is a function that intakes two labels and returns a non-negative number that indicates the extent to which they deviate from one another. So if the labels are continuous, a reasonable loss would be the square difference. The basic statistical learning task is as follows. We are given a training set. That is, m pairs, xi, yi, m labeled instances that we assume are drawn independently from the world's distribution. Given this training set, our goal is to return a hypothesis, also called a predictor or classifier. That's just a function from instances to labels. And we want our predictor to be one that minimizes the population loss. Okay, what is the population loss? That's the average loss, the average discrepancy between the true label and the prediction when labeled instances are distributed according to the world. Okay, that's what we want to minimize. We can't measure this thing given a predictor because we don't know D. But nonetheless, we want to somehow minimize this thing. If you sweep away a lot of the details Basically, the approach in statistical learning is as follows. I predetermine a hypothesis space. That's a set of predictors, a set of functions from instances to labels. I fix that in advance. And given the training set, after seeing the training set, I return the member of this set, the predictor in here, that minimizes the empirical loss. And what is the empirical loss? That's the average loss, the average discrepancy between the true label and the prediction, not over the world's distribution, but over the training set. So this is something that I can actually measure. Given a predictor, I just run through the training set and measure the average loss. What I'm going to return is the predictor in this set that minimizes the empirical loss. And I'm going to hope that this thing has a low population loss. And there are three fundamental factors that determine how well this thing will work. What will be its population loss? And we're going to illustrate this now. In gray, this is the space of all functions, all possible classifiers. Right? And in blue, that's our hypothesis space. That's the set that we predetermined in advance. F star D, this is the perfect predictor. Okay, the one that minimizes the population loss over all possible predictors. It has nothing to do with us. It's just a property of the world, of the problem. H star D, this is something that does have something to do with us, and that is the optimal predictor within our hypothesis space. That's the one that minimizes the population loss. Okay? It does not depend on the training set in any way, only on the problem, on the world, and on our choice of hypothesis space. H star S, this is the predictor that minimizes the empirical loss. Okay? This is something that we theoretically should be able to find. We can just run through all the members in our hypothesis space, measure the empirical loss of each, and this would be the minimizer. In practice, this search is oftentimes difficult, and we can't really perform it exactly. We return some approximation, H bar. The population loss of H bar is governed by three factors. Number one, three sources of error. Number one, approximation error, also called expressiveness. This results from the fact that there's no reason for the hypothesis space that we predetermined to contain the perfect predictor. There is some penalty here. Okay? It's not able to represent everything. It might not be able to represent the perfect predictor. Okay? The second source of error is called estimation error, also referred to as generalization, and this intuitively relates to the fact that the training set is finite. Okay? If the training set were infinite, and we'd have a predictor that does a really good job on the training set, it would also likely do a good job in the real world. But in practice, the training set is very finite, and you could have a predictor that does an excellent job on the training set, but a terrible job in the real world. And that's called overfitting. Yeah, so this is a statistical source of error. And finally, training error, also referred to as optimization. This again results from the fact that we are not always able to find H star S. Sometimes we only find an approximation. So in its basic form, statistical learning theory is about understanding these three factors and how they trade off with one another. And they behave in ways in deep learning that are very, very different from what we're used to in classical machine learning. Okay, so that's what we'll talk about now. So classical machine learning, not a very well-defined term. Apologies to the experts here. You can think of linear models. They just hypotheses that map instances to labels linearly. Okay? In classical machine learning, problems are set up in a way that the empirical loss minimization, the search for H star S, boils down to what is called a convex program. This is a minimization of some loss function that looks like a gigantic bowl, if you will. Okay? We know how to minimize functions that look like bowls, and so we are actually able to find the empirically optimal hypothesis. We're actually able to find H star S. So the training error is pretty much zero. And it's all about the estimation error and the approximation error. And for these, there's a well-known phenomenon. It has different names. One of them is the bias variance trade-off, and what it means intuitively is the following. If I take my hypothesis space and expand it, I make the model richer, then obviously the approximation error goes down. I can represent more. But the estimation error will go up. I will be more prone to overfit. Okay? Overfitting will be more of a problem. There's a classic example of fitting polynomial to points on the plane. If you work with higher degrees, it's easier to fit all the points, but you will learn something that's not meaningful. Okay? So that's a manifestation of this phenomenon. And vice versa, if I make my hypothesis space smaller, the approximation error goes up, I can represent less, but the estimation error goes down, I will be less likely to overfit. And so all in all, I think the theoretical machine learning community had a feeling that we have a decent understanding of what goes on here. And in deep learning, the situation is very, very different. Okay? Deep learning refers to hypothesis space that are composed of transformations, one on top of the other. Each one of them is typically nonlinear. And with these models, the optimization, the empirical loss minimization, is a non-convex program. So you're minimizing a loss function that does not look like a big pole. Has many hills and valleys, very complicated landscape. We actually know that the empirically optimal hypothesis, H star S, is not unique. There are a lot of them. And for some reason that we don't really understand, variance of gradient descent, which is a very simple algorithm that just takes small steps in the direction of steepest descent. These type of algorithms somehow are able to reach the global minimum, somehow are able to find H star S. And we don't really know why. And with expressiveness and generalization, the situation is even more peculiar and different from what we're used to. That is that we know empirically that some empirically optimal hypotheses, some of these H star S's have a low population loss. They generalize well, and others don't. They generalize very poorly. And for some reason, on the type of problems that deep learning works for, the solutions that are returned by variance of gradient descent oftentimes have a low population loss. They generalize well, and we don't really understand why. What is this preference that's implicitly encoded into gradient descent? Maybe more surprisingly is the fact that there seems to not be a bias variance trade-off. And we empirically observe that when you expand your hypothesis space, I guess obviously the approximation error goes down. What we observe empirically is that the estimation error goes down too. Larger models generalize better. And this pretty much goes against our classic intuition. And so overall, I think it's safe to say that we don't really have satisfying answers to these questions. And these are the type of problems that have been interested in the last several years and am interested in now. And I will talk about works that address some of these questions.
If you have enough data.
If you have enough data.
Right.
They generalize well if you have enough data. Yeah.
You have enough data and it's not fake.
If the data is not fake. Yeah, okay, so that all boils down to typical. Okay. Yeah.
These kinds of phenomena, are they, I mean, usually this is what is reported, we applied a deep learning algorithm and we got this result which generalizes well, but people often do not report all the cases where this does not. So what you're describing is when things go well. But, you know, there's a lot of fine-tuning going on and tweaking the deep learning, and how does that fit into this?
Very good question. So I would not write any of these down if I did not personally experience this pretty much all the time. Okay, so these type of phenomena, when you follow standard practices, they are very, very repeatable. It's arguable whether the standard practice is a result of many years of tuning. It probably is, but right now, if you just take out of the box, use deep learning in a standard way, you will see these things clearly.
For any kind of architecture?
No, the type of.
Yeah.
So what kind of the questions that I'm interested in is what is it about the models and algorithms that we use that makes this happen? Okay? What is it about typical here? And maybe if we have this kind of understanding, then we'd be able to relieve ourselves from a lot of these noise and black magic and only focus on the things that matter. But right now, this is kind of an empirical observation. Okay? So anything else before we close this philosophical chapter?
In inverting linear operators, you also have this property of gradient descent, fast inverting large eigenvalues. And this is very clear. So people, unfortunately, I'm not sure they talk about this much. Also gradient, also conjugate gradient has this nice property. You have a ill cost problem, you went to invert it, and they lead you to good solution even if your
Yeah.
operator is huge.
So,
So it's,
people are turning to linear models to try and get intuition. It's things that people are doing. Not all of the phenomena here are.
so your model is to complete what you mentioned in the beginning. Linear model may be huge, and you will overfit when you optimize it exactly. But if you optimize it with gradient or conjugate gradient, you get this nice phenomena that you observe in neural.
That's right. Some of the phenomena that happen here could happen with classical models, but it's not the standard way of our understanding. Okay, so now I'm going to actually talk about concrete works and not just philosophy. This is part of the talk is based on two papers, one from the last ICML and one that will appear in the upcoming ICML. Works were done in Princeton with Sanjeev Arora, Elad Chazan, and students Wei-Hu and Noah Golowich. We will only focus on training here, only on optimization. Okay, I'll talk about approximation here later. Right now, it's all about minimizing the non-convex objectives that we get with deep networks. We're going to start by kind of reflecting on an approach to optimization in deep learning that's very popular, and we're going to argue that it is not entirely sufficient and that more factors should be taken into account, and then we're going to do that and show some stuff. Okay? So the prominent approach for understanding optimization in deep learning is based on geometry, on the geometry of the loss landscape, and in particular on its critical points. That's points where the gradient vanishes. Okay? So you could have different types of critical points. For example, you could have a local minima that is good, meaning that the objective value is close to the global minimum. You could have a local minimum that is bad, so the objective is much higher. You could have a saddle that's not a local minimum, and the saddle could be strict, meaning that there are directions of significant descent, or formally, the Hessian has negative eigenvalues, for those that know. Or you could have a non-strict saddle, which is very flat, and if you want to start the descent, you have to walk significant distance. Yeah, this is the case where the Hessian does not have any negative eigenvalues. Right? A result that was shown by different people and different flavors more or less says the following. If, number one, you don't have any poor local minima, and number two, you don't have any non-strict saddles, then gradient descent will converge to the global minimum. Okay, so this sounds pretty intuitive, maybe. Essentially means that gradient descent is not going to get stuck at saddles that look like this. There is some technical legwork to do here, but this is the result. And motivated by this result, a lot of people focused on showing, proving properties 1 and 2. Okay, so Daniel, I don't know if he's here, but he has some works on this, both 1 and 2, other people as well. And this kind of approach has led to proofs that gradient descent converges to global minimum for shallow models, 2 layers. Okay? It did not work for deep models, 3 or more layers, and there are several reasons for this. First of all, condition number 2, the fact that there are no non-strict saddles is just false. If you have 3 or more layers, then for example, when all the weights are 0, all the second derivatives are 0, and there you go, there's a non-strict saddle. A very flat saddle around the origin. Okay, so this kind of approach hits a wall right at the outset. A more general argument against purely geometric approaches is the fact that in practice we see that different algorithmic factors, for example, the type of initialization, profoundly impacts the solution that gradient descent finds. And if you're trying to show that the entire geometry, the entire landscape is nice, it's going to be difficult to capture these type of phenomena because you are trying to show that the objective is nice, and that would mean that wherever you initialize, you're going to hit a good solution. Okay, but it's not what happens in practice. In practice, different trajectories seem to lead to qualitatively different results, and the only way to account for this is to take into account the algorithm and the type of initializations that are being used. Okay, take into account the specific trajectories. And this is something that people have begun doing recently, and they managed to show for different settings convergence of gradient descent to global minimum with shallow models, 2 layers. What we're going to do is follow this approach for deep models, arbitrarily deep. And specifically, it will be linear neural networks. And I'll explain what that means.
Are you talking about stochastic gradient? Yes?
No,
No.
no, gradient descent.
Okay.
That's a question whether the S there, the stochasticity, how important it is. It depends on who you ask. Some of the works here treat SGD, some treat GD. I'm going to talk about gradient descent. Okay? But in any case, when I say that it didn't work for deep, I mean both GD or SGD. For now, just think of SGD as a variant of GD. Okay, so let's now talk about convergence and gradient descent for linear neural networks. What's a linear neural network? In the deep learning jargon, it's a fully connected neural network with linear activation. And in the human being jargon, it's just a sequence of matrix multiplications. Okay, that's all there is to it. The input is mapped to the output linearly, but it is parameterized as a sequence of matrix multiplications. So even though the model is linear, when you run gradient descent over this parametrization, it's highly non-convex. Okay? And for this reason, this problem is extensively studied. It's viewed as a surrogate for optimization in deep learning. Gradient descent over a linear neural network. Okay? The state-of-the-art result in this problem is by Bartlett et al. From the last ICML. What they show is that for the special case of linear residual networks, that's a special case where all the matrices are squared, all the hidden dimensions are the same, and all the matrices are initialized to identity. For this special case, when you use L2 loss, meaning that the loss is the squared Euclidean distance between the true label and the prediction, for certain types of data sets, gradient descent efficiently converges to global minimum. Okay, so it's a fairly specific setting. The analysis is very specific as well. It takes into account the specific properties of identity initialization and symmetry and things like that. But nonetheless, this is the only existing result that I'm aware of that shows efficient convergence of any variant of gradient descent to global minimum over a deep model, 3 or more layer model. Okay, so a word about efficient here. There are some results that show polynomial time, or where the network has polynomial size. They do show this kind of convergence. But the polynomial is like number of examples to the power of 56 and things like that. So when I mean efficient, I mean something that we see ourselves actually running on a computer and converging in feasible time. Okay? So it's fairly limited, but this is the best that we have right now, and we're going to derive something much more general than this. Okay? All right, so we're going to start by considering gradient flow. Gradient flow is kind of a continuous version of gradient descent. It's what you get when you take the step size, the learning rate, to be very small. It's a differential equation. Okay? At every point, we're following a curve that at every point in time, its direction is the opposite of the gradient. Okay? So gradient descent is these discrete steps. Gradient flow is this continuous curve. And we're going to analyze this and use it as a stepping stone towards gradient descent. Okay? The advantage of gradient flow is that it allows the use of different mathematical tools that are more difficult to apply with gradient descent. Okay? Differential equations, differential geometry, and you can perform the analysis using these tools, and then if you work hard, you can extend ideas and results to the discrete settings. And that's what we're going to do. Okay, so we're thinking about the trajectories of gradient flow over a linear neural network. The objective that we're going to optimize with gradient flow looks like this. We have a loss for a linear model. So this could be L2 loss or hinge loss, cross entropy loss, whatever. Usually it's a convex loss. And this loss induces a non-convex over-parameterized objective for the linear neural network. Okay, the objective over all the weights is just obtained by taking the weight matrices, multiplying them by one another, and plugging into the original loss. So we are running gradient flow over this type of objective. Okay? Definition. We say that the weights W1 to Wn are balanced if the following equality holds for every j. For every layer j, the weight matrix of layer j plus 1 transpose times itself is equal to the weight matrix of layer j times its transpose. Okay? This needs to happen for every j, for all the layers, in order for them to be considered balanced. Okay? So right now this is just a definition. It has different implications. For example, the singular values of wj plus 1 are equal to those of wj. But for now it's just a definition. The reason it is interesting is that with the type of initializations that people oftentimes use, this is either met exactly or approximately. If you initialize weights to be close to 0, then this is approximately met. And if you initialize them to the identity, this residual is saying that this is met exactly. And what we show is that gradient flow preserves balancedness. So if you initialize it with weights being balanced, and you run gradient flow, the weights are going to remain balanced throughout the entire optimization path. Okay? Gradient flow does not move arbitrarily in space. It follows specific paths, in particular balanced paths. Okay? So things behave in a regular way. And we're going to use this to prove things. Right? This is something that requires taking into account the specific trajectories of gradient flow. The fact that along these trajectories weights are balanced if they were initialized that way has different implications, and we're going to show it. Okay? Okay, so the first question that we ask is the following. When we run gradient flow over a linear neural network, gradient flow over this type of objective, then at every point in time, there is an equivalent linear model. It's just the multiplication of all the matrices. That's the end-to-end model. And it moves in space according to some dynamics. These dynamics are not gradient flow over the loss, because we're not running gradient flow over the loss of a linear model. We're over-parameterizing and using a deep linear network and running gradient flow on that. So how does this thing move? Okay. The answer is the following. If the weights W1 to Wn are balanced at initialization, then the end-to-end model follows what we call the end-to-end dynamics. This is what's written here. If you ignore the blue term, then what you see here is just gradient flow over the loss. Okay, vec just means to arrange a matrix as a vector. It's not important if you don't have this term. So without this term, what's written here would just be gradient flow over the loss. This term, that's what reflects the fact that we use the deep linear network. And what this term is a preconditioner. Okay, that's something very, very popular in optimization. There are different types of preconditioners. Newton's method, for example, is a special case. It's based on second derivatives. And here the preconditioner has a closed form expression. And I'll talk about that in a second. Preconditioners in general, what they do is it's a PSD matrix that you multiply the gradient with before you use it. So you stretch the gradient by different extents in different directions before you use it. Okay, you kind of warp the gradient before you use it. And this specific warp has a specific structure. Qualitatively, what it does is it kind of reinforces the directions that the optimization has already taken. Okay, you're optimizing this end-to-end model implicitly according to these dynamics. It moves in space. And at every point in time, the singular directions that are prominent in where you are in parameter space, these are the directions that are stretched more significantly. So it's kind of an acceleration, kind of a momentum effect going on here. And for those that know, there's actually a concrete relation to momentum. We formalized this in the paper. Okay, but the bottom line is that if we had a linear model and some loss, and instead of running gradient flow on that linear model, we were to run gradient flow over a linear network, it's kind of an over-parametrization that's obtained by adding redundant layers. Running gradient flow on that implicitly induces a preconditioner that promotes movement in directions already taken. And this is going to be useful for showing different things. Okay. Starting with convergence to global optimum. So this is the end-to-end dynamics. This is our preconditioner. We have a closed form expression for it. One of the things we know is that if the end-to-end model, if the matrix has full rank, then this preconditioner has full rank as well. I'm telling you this. It's a direct implication of the closed form expression that we have for the preconditioner. And what it means is the following. As long as the preconditioner is full rank, the loss is going to continue to decrease until this gradient, until this term is 0. Okay, so in general, the loss will decrease until the gradient is 0. Or maybe this preconditioner stopped being positive definite. It stopped being full rank, which means that the end-to-end model is singular. So if you run gradient flow and you never hit singularity, you're going to eventually reach a point where this gradient is 0. Typically, the loss function that people use, this L, is convex. Not the objective over the linear network, but the loss over the linear model is convex, L2 or cross entropy. And that means that condition 1 implies that global minimum was reached. So if you run gradient flow, you had a convex loss, and you replace your linear model by a deep linear network, and you run gradient flow over this thing, if you never hit singularity, you're going to eventually reach the global minimum. Okay, so this is what this corollary says. We have a loss, it's convex, and we optimize the linear neural network with gradient flow such that 1, weights are balanced, and 2, the initial loss is smaller than the loss of any singular matrix. So by reducing the loss, decreasing it, we're not going to hit singularity. Therefore, at some point, condition 1 is going to happen, and that means that we've reached global minimum. So what we have here is the result for gradient flow reaching global minimum under 2 assumptions on initialization. There is no notion of computational efficiency here because this is a continuous optimization process. What we're going to do now is extend this thing to gradient descent.
I mean, the first condition is something you can implement, but the second one seems kind of hard to guarantee. I mean, how do you know? I mean, how can you fulfill the second condition?
It's a good question. I'll talk about it, but let's put it this way. This is a condition of how good your loss is when you initialize. For the case where the network has output that's one-dimensional, scalar, half of the spit, if you initialize close to 0, with probability half, this condition is met. I'll talk about this when we move along, but it's not a hard condition. I'll talk about this in the gradient descent setting. Okay, we're going to require a little bit more than that, and I'll show that that's not, or I'll tell you that that's something that is met with significant probability under random initialization. So we want to extend the result from gradient flow to gradient descent. The result for gradient flow made 2 assumptions on initialization. Number 1, we assume that weights are balanced. So for every j, wj plus 1 transpose times wj is equal to wj transpose. That's an assumption. I might as well write it this way. Instead of saying that these 2 things are equal, I just say that the norm of their difference is 0. That's the first assumption. The second one was what Ron just asked about, and that's the loss is smaller at initialization. The loss is smaller than the loss of any singular solution. Okay? So the loss of the initial end-to-end matrix is smaller than the loss of any matrix that has a 0 singular value. What we're going to do is define discrete versions of these conditions, and that's going to facilitate the result for gradient descent. So the first thing we do is we allow this norm to not be 0, but be small. Okay? Instead of requiring that this norm be 0 for every j, we require that it be smaller than some delta for every j. And we call this delta balanced. The smaller delta is, the closer you are to this condition. Delta is 0, that means that you have perfect balances. Okay? So that's the first discretization that we made. The second one is the following. Instead of requiring that the initial loss be smaller than the loss of any singular solution, of any matrix that has a 0 singular value, we require something a little bit stronger. We want the loss at initialization to be smaller than the loss of any matrix that is almost singular, okay, that has a singular value smaller than C. The larger C is, the harder it is to meet this condition. And if C is really, really small, close to 0, then you recover the original condition. Okay, we call this, if this is met with some C, we call this a deficiency margin of C. Okay, so now we have these discrete versions of our assumptions for gradient flow: delta balanceness and deficiency margin. Now we can state the result for gradient descent. And the result is following. We prove this for the case of L2 loss. It's a very common choice. In this case, the loss is the squared Euclidean distance between the true label and the prediction. And what we prove is the following. Assume that you run gradient descent over the linear neural network, and that the weights at initialization have a deficiency margin of C, and are delta balanced with a delta that scales like C squared. Under these two conditions, if you run gradient descent with a learning rate that scales like C to the fourth, then the loss decreases to global minimum exponentially fast. It moves like e to the minus constant times t. Okay, this is called linear rate convergence. It's very, very fast convergence. Okay, so this is the result that we have. Convergence of gradient descent to global minimum at a linear rate under two assumptions on initialization. Okay. Let's say a few words about these assumptions. So, by the way, how long do I...
20 more minutes.
20 more minutes? Okay, good. Yeah, we'll start in 11. Okay, so what can we say about these assumptions? First of all, they're both in some sense necessary. And what I mean by that is that if you take this theorem and erase one of these conditions, then it's false. Convergence will not necessarily take place. I can easily construct cases where things will diverge or not, or the loss is going to be lower bounded by some constant. Okay, so you can't just throw away one of these conditions and hope to prove something like this. You have to put in some other assumption. Okay, so that's the first thing to note. The second is what you asked on, and that is the following. For the case of an output dimension 1, when your network is predicting some scalar, if you use a random initialization that is not exactly what people use, but pretty similar, we call the balanced initialization, then these two conditions hold with constant probability, and by constant I mean 0.5, not some constant. So, for output dimension 1, if you use this random initialization, with probability at least 0.5, you will get linear rate convergence to global minimum. No assumptions at all. Okay? Overall, this is the most general guarantee that I'm aware of for gradient descent reaching global minimum efficiently over a deep, that's a 3-layer or more model. Okay? Okay, so what we're
Can I ask about the proof? I mean, are you using approximation to the continuous
Great
flow
question.
or
Great
direct?
question. Okay, so right now we're repeating the same ideas discretely from the outset. It's not that we're taking something as is and translating. This is something that I am working on right now, a general translation between gradient flow and gradient descent. What we did there is just work very hard and repeat all the steps of the proof discretely. But it's the exact same ideas there. Okay, so in this case, continuous mathematics served as inspiration and gave us ideas. That's a good question. Okay, what we're going to see now is something that I think is more interesting or surprising, and that is the role of depth. Okay, so typically people view depth in deep learning as something that boosts expressiveness. Okay, it allows you to represent more. We all know these, or maybe at least half of us know these illustrations where deeper layers are able to capture more abstract concepts. This can be formalized, and I'll talk about that. In terms of optimization, people believe that depth makes it more complicated. It turns convex problems non-convex. You're now dealing with a problem that we don't have any guarantee for, and it's non-convex, hence we believe it's more difficult. What we're going to see is that this is not always the case. So we're going to talk about the effect of depth for linear neural networks. So this is the end-to-end dynamics that we derived for gradient flow. That's our preconditioner. This is a discrete version of it. That's the preconditioner, and now it's discrete steps. These kind of preconditioned gradient descent. What we show is the following. For any p greater than 2, there exist settings where the loss is the LP loss. So it's the difference between the true label and the prediction, the p norm of this thing to the power of p. This is a convex loss. there exist settings with this loss where the end-to-end dynamics reach global minimum much, much faster than gradient descent. Okay, so I can create cases and data sets where the optimization problem with a linear model, it's a convex problem, and you can run gradient descent on that. But if, alternatively, you did something crazy, and that's replace the linear model by a deep linear network, run gradient descent on that, even though it doesn't give you anything in terms of representation, it just makes optimization seemingly more complicated, there are settings where this will actually accelerate optimization significantly. And we prove this by kind of creating these cases where gradient descent fluctuates wildly, and this preconditioner helps avoid that. So we see that theoretically, there are settings where non-convexity could actually be a good thing. Okay, but the impact of such a statement is limited because I am carefully constructing these settings where non-convexity helps. It doesn't mean a lot about settings that we encounter in practice, and for that we run experiments. Okay, so this is experiments with linear neural networks. We take a standard regression problem from UCI machine learning repository. We use L4 loss, it's p greater than 2. And this is what you get when you compare a gradient descent over a one-layer model. This is a convex problem. Compare that to gradient descent over a two-layer model. It's a non-convex problem. And a three-layer model, also a non-convex problem that we tend to think of as more difficult. You see here that depth, even though it doesn't give you anything in terms of expressiveness, and it makes optimization non-convex, in this setting, it accelerates gradient descent significantly. Okay, so this is something that's very non-intuitive for us right now. Okay, in the way we view non-convexity, we tend to think of it as a terrible thing. But apparently sometimes it's terrible, but sometimes it could actually be a good thing. Okay? There are different types of non-convexities. What we did next is compare this implicit acceleration of gradient of depth of non-convexity to explicit acceleration methods that people design for convex problems. So specifically, you compare to Avogadro Nadav delta. You can see that in this case, the implicit acceleration of depth of non-convexity outperforms explicit acceleration methods for convex problems that people work very hard to design. And so this is something that's fairly surprising. The next thing we did is run experiments with nonlinear neural networks. This is something we don't have theory for, just an experiment.
Are you planning to look like conjugate gradients?
Am I planning to?
For this comparison?
What, compare this to conjugate gradient?
Conjugate gradient for linear model and for
We didn't do that. We
cascade
didn't
model.
do that. We kind of compared the. Yeah.
The iteration can be, it's not
In
the
both
speed,
you give.
it's not the runtime, it's just the iteration.
Great question. So what you're saying is, okay, maybe I reduce the number of iterations, but I pay per iterate. Every iteration requires more.
Of course.
So the answer is no. And in this specific case, there's a single output to the network. And actually every layer here, just to make that point, every layer here is just a scalar. And still this happens. So the overhead is almost zero. Okay? That's a good question. Okay, so for nonlinear nets, we took the convnet that's built into TensorFlow for MNIST. For those that know, convolutional layers, ReLU, max pooling, then dense layers, trained with stochastic gradient descent and momentum, and it has dropout, whatever that means. And we over-parameterized by adding linear layers after every dense layer. Okay, we took every dense layer and we just added a linear layer. So we added parameters, we added depth, but we didn't change expressiveness at all. And this is what we got in this case. So with 15% addition in the number of parameters, making your optimization problem seemingly more complicated without getting anything in terms of expressiveness gave acceleration by orders of magnitude here. Okay, so this kind of demonstrates that the phenomenon goes beyond just the linear nets that we analyzed.
Why is it so noisy?
Because it's stochastic in this case. This is the batch loss stochastic gradient descent after this one was going to go.
What happens to generalization in this?
It's a great question. So in this case, it followed the same trend. That's just an observation in this case. I don't have theory to show you that. But we're only focusing on optimization now. It's a fair argument saying that maybe your optimization is faster, but your generalization is terrible. That wasn't the case here. In the linear models, it was never the case because you reach the global optimum, it's just one. It was a convex problem, so that's a good question. It didn't happen here.
One more question. What happens if your landscape is noisy? You come to the same place and the same landscape, but you get different result? Or images are noisy or whatever?
What do you mean noisy landscape?
Noisy when you take the same, go to the same place, you get different results. You take the same picture of the same place, you had 100 images before. They're noisy, you don't get the same result every time.
The images are noisy? So the images, the data induces an optimization problem, as far as I'm concerned, the way I look at it. Now you can ask, what do I require from the optimization problem for these things to happen?
Yeah. Yeah.
Okay, so for the linear case, pretty much everything we tried with LP with P greater than 2, it happened. And the more ill-conditioned things were, the more significant the phenomenon was. Okay, but okay. All right, so that was the main part. I'm now going to go briefly over a series of works on expressiveness. I gave a talk here about a year and a half ago. I'm sure you were all here and all remember. So I'm going to go through this pretty quickly. Okay. This is a long series of works starting from 2016 up until today. These were done with collaborators in the Hebrew University. I'm Shashua, my supervisor, and students. And we will now only talk about approximation here, only about expressiveness, the ability to represent functions. Okay? So we talked about linear neural networks. They can be viewed as a matrix decomposition. Okay? We're representing an end-to-end matrix as a sequence of matrix multiplications. Okay? So in the graphical language of decomposing arrays, this is represented this way. Okay? So you have an overall matrix with two edges, two outgoing edges, and it is composed of individual nodes. These are the matrix parameters. That's a matrix decomposition. And this kind of graphical language can describe much more complicated decompositions of tensors, of multidimensional arrays. And you can have different types of topologies that are decomposing the array. You could have trees or trains or other types of structures. And what we show is that just like a linear neural network corresponds to a matrix decomposition, these type of tensor decompositions correspond to other types of neural networks. So a tree, for example, corresponds to a convolutional network, for those that know. And a train corresponds to a recurrent network. This is the most popular architecture for image processing, and this I would say is for sequence processing. And there's a one-to-one correspondence between the structure of the network and the structure of this decomposition. These models are not exactly the kind of models that are most frequently used today. They're arithmetic. Okay? All the nonlinearities come from products. These are kind of polynomial networks. So for example, in the convolutional network, there is no value. It's a linear activation. And the nonlinearity comes from a product. You take, instead of taking maximum from pooling windows, you take their products. Okay? Hierarchical tensor decompositions, that's something that's widely used in different areas of mathematics and also in quantum physics. And we adopted tools from these domains. We also proved several new results to study the expressiveness of arithmetic neural nets, and specifically convolutional arithmetic neural nets. We show different things. For example, almost every function realized by a deep model, if you try to replicate that function or even approximate it with a shallow model, that shallow model would have to be exponentially large. So, put differently, if you randomize the weights of a deep model by continuous distribution, with probability 1, you get a function that you can't realize without depth. It is a very strong form of depth separation. It's the strongest that I'm aware of. Other things we showed are, for example, that if you take your convolutional network and you make the deep layers wider, then you enhance the network's ability to model correlation between pixels that are far away in the image space. On the other hand, if you make the early layers wider, then you enhance the ability to model correlation between pixels that are nearby. And also, in terms of the pooling geometry, pixels that are pooled together early can have stronger correlation. So these two results, theoretical results, translate to guidelines for designing your network in accordance with something you know on a task at hand. For example, and we show this empirically, if I have a medical imaging task and I want to detect symmetry, so I want to model correlation between pixels on reflecting sides of the image, then I might be better off making my deeper layers wider and pooling together entries from opposite sides of the image. We show that this actually boosts performance, and we show other cases as well. So this is kind of a small step towards theoretical analysis, actually giving us concrete guidelines that will allow a less voodoo and trial and error design process. There's still a long way to go. This is a step in this direction. Other people built on our framework connecting neural networks and tensor decompositions to study expressiveness of other models, other arithmetic neural nets, so convolutional and also recurrent. This is a sample of works from the last year. And let's see if we're good with time. I have about 5 minutes to conclude. Any questions at this point? Okay.
So this is done using analysis of the correlation matrix or something like that? How do you show?
What is correlation between pixels? That's a really good question. So it's a delicate point because this is not necessarily statistical setting. Let's put it this way. If I have a function over 2 variables, okay, then if the function is separable, then that's, in statistical setting, that's independence, right? It's a product of 2 PDFs. And in non-statistical settings, the way that you can quantify dependency is by distance from separability. Okay, so mutual information in the statistical setting, that's a KL distance from separable distribution. You can define other distances. Actually, that's what they do in quantum physics. I was hoping to sweep these kind of details under the rug. But, thanks for forcing me to talk. Okay. All right, so let's conclude. So understanding deep learning calls for addressing 3 fundamental questions: expressiveness, optimization, and generalization. When we talk about optimization, we argued that only looking at the landscape, only looking at the geometry is insufficient for treating deep models, 3 or more layer models. And for that, you have to take into account the specific trajectories that the optimizer takes. We did this for gradient descent over deep linear neural networks. We derived what is, to the best of my knowledge, the most general guarantee of efficient convergence of gradient descent to global minimum over a deep model. And maybe more surprisingly is that we showed that depth, in this case, induces a preconditioner that can accelerate optimization, even without any gain in expressiveness, and despite introducing non-convexity. With expressiveness, we showed, or maybe I told you, that just like linear neural nets correspond to matrix decompositions, tensor decompositions correspond to arithmetic neural nets. And then you could adopt tools from different areas of mathematics and quantum physics to study the expressiveness of these models. And a word about arithmetic neural nets. So these are nice models that we can analyze, prove different things on, but they're not just theoretical entities. They actually work well in practice. We have implementations of them in Caffe and TensorFlow, which are 2 of the leading deep learning toolboxes. It's on GitHub, you can see it here. We show that these models reach more than 90% on CFAR10. For those that don't know, this is pretty much where state-of-the-art was maybe 3-4 years ago. Way better than anything that's not deep learning. And we also show that for other types of settings, for example, when you have missing data, then you could get state-of-the-art performance with arithmetic neural nets. And this all leads me to believe that there's nothing sacred about the exact tricks of the trade that people use today. So today it's ReLU, this afternoon it'll be leaky ReLU, and tomorrow LU, or a lot of different variants. They all work well, little differences. These models, arithmetic neural nets, I think they definitely capture the essence of deep learning. Hey, they're not state-of-the-art right now. Maybe if Facebook would decide that they're important, they will be state-of-the-art, but they definitely capture the essence. And so I think that if we understand these models, that would be a significant step forward in terms of our understanding of deep learning. And accordingly, that's kind of my goal, has been for the last several years, and is these days. Want to analyze expressiveness, optimization, generalization for arithmetic neural nets. Here's an illustration of a roadmap to get there. Okay, so we have linear neural networks, matrix decompositions. This is kind of a toy alpha model for arithmetic neural nets, which are tensor decompositions, and actually work well in practice. Have expressiveness, optimization, and generalization. So for linear neural nets, expressiveness is trivial, it's just linear. Optimization is what we talked about. We have kind of a footstep. Don't understand everything, but we've begun. For arithmetic neural nets, expressiveness is what I briefly went through in the last part of the talk. We have a footstep here too. Optimization for arithmetic neural nets is something that I'm working on now. Essentially what we're trying to do is translate the characterizations of gradient flow and gradient descent trajectories over matrix decompositions, extend that to tensor decompositions. And some of the results actually transfer. For example, balancedness. Just like we saw that gradient descent or gradient flow maintains balancedness over matrices, if you run it on a tensor decomposition, it would maintain balancedness over these individual nodes that we saw. In terms of generalization, we're now working on generalization for linear nets, and the setting that we're considering here is matrix completion. Okay, you have some low-rank matrix, and you observe a small number of entries from that matrix and you want to complete it. And what you do is instantiate a linear neural network, kind of a sequence of matrix multiplications, and run gradient descent over this thing. Apparently, it induces a certain regularization term that we have a closed form expression for. So we can actually see the kind of inductive bias going on here. And over the course of the next 2, 3, 4 years, my hope is to have a strong footstep in each and every one of these anchors, and then hopefully have a deep learning model that we have a better understanding of and also works well in practice. I think that would be a step forward. And kind of looking farther ahead, everything I talked about today falls into the category of supervised learning, theory for supervised learning. Okay? And in supervised learning, practice is way before theory, right? Things work very well long before we understood them. We actually still don't. But if you want to reach strong AI, human level artificial intelligence, then supervised learning is not all there is to it. A lot of the people here, I don't have to tell them that. There are other settings that much more closely resemble human level intelligence. For example, semi-supervised learning. Right? When you teach a child what a dog is, then you show them 10, 20 examples of dogs and tell them that this is a dog. But then they see a lot of other dogs, and no one tells them that these are dogs, but they can still extract information and learn from that. This is a more kind of realistic setting. And beyond that, there's reinforcement learning and control. There are a lot of people here are working on this, and here you're not just training a passive model to make predictions and tell you what it thinks. It's actually operating in a dynamic environment and making decisions. So this is a very general setting. We are reinforcement learning agents, if you will. In these two settings, semi-supervised learning and reinforcement learning, I will carefully say, here I should be very careful, that the practical success is not as developed as it is in supervised learning. Okay, there's still a way to go before we regard these settings as solved problems. Okay, and I believe that maybe in these two settings, as opposed to supervised learning, maybe next big leaps, or some of them, will come from some form of theoretical understanding or some insights. And I believe that to do this, we will, or we may need to adopt tools from scientific domains that we're not necessarily used to. Okay, I'll give you a couple of examples of things that arose from our works. So, for example, hierarchical tensor decompositions induce certain probabilistic models that you can use to model a distribution of data. We use that for the missing data setting that I talked about. Got very good results. It could also be used for semi-supervised learning. This is something that we're thinking about. And in terms of reinforcement learning, again, carefully, I would say that most of the, or many of the success stories that we hear about are model-based. There's some model for the environment. And it's a challenge building a model for the environment. When you're playing a game like Go, then maybe it's easier, but in general, we don't know how to do this. And I think that there are different concepts and tools from physics that we can use here. Okay, so with regards to the question on correlation, in quantum physics, they have an entire industry around characterizing what is physical and what is not. and quantifying that and having computational tools to measure that. We use that for studying the ability of neural nets to model correlation. I think it could also be used to model physical environments, things like entanglement, dependencies, time evolution, and I believe that this may pave way to being able to create models that are informative and specific enough for us to prove things about and develop algorithms for, and yet are general enough to capture various settings. Okay? And in general, I anticipate that in the years and decades to come, modeling, being able to model data or environments is going to be very, very important, because in statistical learning theory, a lot of people are maybe a little bit averse to making assumptions. We like things that are assumption-free and general, but that naturally leads to worst-case results. And in deep learning, we know that the worst case fails. So we're going to have to start making assumptions and modeling. I believe that tools from other domains may be key here, and that this might help us reach strong AI. Thanks. All right.
Questions?
Very nice results. Is there any relation between the balancing conditions to practical stuff people usually do to train models?
Okay, good. So for linear nets, I'm kind of showing theoretically that it's in some sense necessary. I think there's something general here that does carry over to neural networks in general. Empirically, when you try to initialize your model with one matrix being very small and another being very large, typically it's not going to converge. So I think that there is something general here. One of my collaborators extended some weak notion of R-balancedness to models with ReLU. I think it's something deep and profound. We kind of formalized everything related to it for linear nets, but I do think it's
Connection to which normalization?
whether this can. So Sanjeev has work on that, the connection between balancedness and batch normalization. I'll have to think about that, and it's not something I thought of up to this point.
So let's end. Thank you.